Okay, so we're going to talk a little bit more about our shaping of histograms and how we can get certain pieces of information. Okay, so we're going to go back and discuss this bell-shaped curve, or what's called a symmetric. Okay, now we referenced this as symmetric earlier. We're not going to call it bell-shaped because it does kind of have this top of the bell, and then it comes out and kind of flares out just a little bit at the bottom. Okay, now with a bell-shaped set of data, we do have a set of values that kind of help us out as we're processing here, okay? So we have what's called the empirical rule. And with the empirical rule, what we know is that if I go from the center of my data, which is my mean, and I go from that value, one standard deviation up and one standard deviation down, that between those two values, approximately 68% of the original data set will be within those two values. If we go 2 deviations above and 2 deviations below, then approximately 95% of my data lives within that. And if we go out to 3 up and 3 down, it's all or almost all of our original data set will be between there. So what we're going to do is we're going to look at examples 3 and 4, and then we're going to jump over to another one. And I'm going to show you how to set this up so that you can make sure that you understand where this is going, okay, and how to kind of solve these things, okay? So I've got my prettiness here. Here's my pretty bell. Here's my middle, and then I'm going to draw 1, 2, 3 above and 1, 2, 3 below. Now, what they tell us on number 3 is they tell us that the mean is 77, and we have a standard deviation, and we're going to use S here for this one, of 8. Okay. So what we're going to do is right here in the middle, we're going to put 77, and then we're going to add 8, and that's going to put me at 85. And again, I'm going to add 8, and that'll put me at 93, and I'll add 8, and that'll put me at 101. Now, coming this way, I'm going to subtract 8. That'll put me at 69. Subtract 8, I'll be at 61. Subtract 8, and I'll be at 53. So I have my setup here, okay? And so what they're now discussing is if I am from here to here, that is 68% of my data. If I push out to 61 to 93, that's 95% of my data. And if I push all the way out to 53 to 101, we're at all or almost all. Okay, so what happens here is on number 3, it says assume that it's bell-shaped, approximately what percentage of values are between 53 and 101. Now that is 1, 2, 3 standard deviations below and 1, 2, 3 standard deviations up. Since that is our 3 standard deviations away, that is or almost all of our data is between those two values. Okay. Now it says assume for number 4 that it's still bell-shaped. Between the two values will 68%. So when I look, 68% is right here in the middle, and that ran from 1 below to 1 above. So 68% is 1 standard deviation away, which is the value 69 to 85, okay? And this is really the 2 styles of questions you're going to see. One is they're going to give you 2 values, like the 53 and the 101, and ask you what percentage falls between that. The other option is going to be they give you a percentage and they want you to reference back to what those values are. Now, what I want you to know is for the purpose of a test, I'm going to stick with that 1, 2, or 3 out. So it's going to be 68, 95, all or almost all. But you may encounter, and I'm going to put this up here, an instance where they want you to do kind of a partial up or a difference up, difference down, okay? So we talked about that between these first 2 is 68%. Now, because this is symmetric, that means this is 34% and 34% when that happens. Okay. Now, between 2 up and 2 down, we have 95%. Okay. Now, if we were to take the 95 and subtract the 68, that leaves us 27%. And when we cut that down, this is 13.5 and 13.5, because again, it has to be symmetric. Now, these outside two numbers, okay, are going to be 2.35 and 0.15. Okay, so now if we take a look at number 8, okay, it says a study is conducted at the Center for Population Economics at the University of Chicago, and they studied the birth weights of 607 babies born in New York. The mean weight was 3541 with a standard deviation of 852. Okay, so the first thing that we're going to do is we're going to set up our chart. So 3541 is going to go right here in the middle. I'm going to add 852 to that. So I've got 4393 down just a smidge. So we can do that. 5245 and 6097. And then we're going to subtract . Okay, so now the first question asks us, it says, estimate the number of newborns whose weight is less than 4393. So they want us to go from here down. Okay, and so the way I'm going to do that is I'm going to add 34, 34, 13.5 plus our 2.35 and our 0.15. And when we add all that together, we get 84. So it's 84%. Now, they want us to know the number of newborns. So what we're going to do is we're going to take 0.84 and we're going to multiply it with the 607 babies. And that gives us 509.88, which we would send up to 510 babies. Okay. Now, for part B, it says estimate the number of newborns whose weight was greater than, okay, so I'm going to get rid of my little blue arrow, my purple arrow here, greater than 1837. So I want to go from here up. So for that one, I'm going to do 13.5, 34, 34, another 13.5 on the other side, 2.35, and our 0.15. And we get 97.5%. So again, they want to know the number of them. So 0.975 times our 607 is going to give me 591.825. So we would say 592 babies. Okay. So the last one asks us, okay, and again, I'm going to get rid of my blue arrow here. We want to be between 1341 and 5245. So I'm going to add my 34 and my 13.5, which is going to give me 47.5%, 0.475 times our 607 gives me 288.325. So I would say 288 babies. Okay. So this is, you can now see how they will do this where they want like different portions or different sections. Again, I'm going to stick with 68, 95, all or almost all when I ask my questions with this, but you may see a couple of these where they ask the partial bits in some of the homeworks. Okay. Now, the empirical rule is great as long as we are working with a bell-shaped data set. However, if it is not bell-shaped on our data set, then we cannot use the empirical rule. Okay. So there was a mathematician named Chebychev that basically he wanted to do a little better, okay, than just, well, I don't know, okay, because this bell curve was there and it was great when that was all happening, but he wanted to be able to talk about any data set, okay? So what he came up with was a at least statement. So basically he's kind of lowballing it and saying at a bare minimum, you're going to get this, okay? But his inequality holds for any data set, okay? So the way this works is, and I'm going to rewrite this formula because that is not quite right. Somehow the fraction didn't quite pull correctly on this. So the formula is, and I'm going to switch over here so that you can see this. Okay. The actual formula is 1 minus 1 over k squared. And this is going to give you a fraction that you can then convert to decimal and then push out to percentage. But his says at least this much. Okay, so Chevy is super, super big on at least. Okay, so if we take a look at number 5 on our worksheet, okay, it says if we do not assume that the histogram is bell-shaped, at least what percentage of values will be between 53 and 101? Now, guys, this was back on our bell curve where we had the 77 in the middle and 101 was up here and 53 was down here. And it was 3 up and down, which means when they're asking this, K is 3. Now, with Chevy, it has to be the same amount up and down because there's only one spot for me to put this in on. So I'm going to do 1 over 3 squared, which 1 minus 1/9, which is 8/9. That in decimal is 0.888, repeating basically. So that's going to be 88.9%. And again, this is at least this much. Okay. So let's take a look at number 9. Okay. So it says the Energy Information Administration records the price of electricity in the United States each month. In July of 2013, the average price was $10.16, 10.16 cents per kilowatt hour. Suppose that standard deviation of 1.06 per kilowatt hour. What can you determine about the data using Chebychev's inequality? So they outright tell me that with K equal to 2. Okay, so this is, again, I'm just straight plugging in. This is 1 minus 1 over 4, which is 3/4 or 0.75. So at least 75% is what Chebychev's is going to tell us for that one. So at least, again, with the Chebychev's thing with this, okay? Now, one other thing that we'll talk about in this section is what's called a coefficient of variation. Now, what this coefficient of variation tells us is how large the standard deviation is by comparison to the mean, okay? What this can do is it can help me determine, again, how spread out something is. So, for example, if we're talking about SAT and ACT scores, SAT scores are out of like 1,600. So I expect that the mean is going to be higher, but that standard deviation may also be bigger just because the scores are bigger numbers as opposed to ACT, where the high score is only a 36. So I would anticipate that because the biggest score or the highest score is only a 36, that standard deviation, I'm not going to have a standard deviation of 20. Okay, that's not going to happen. But I might have a standard deviation of 20 or 40 or 60 or whatever on an SAT setup. Okay, so the way that we find this is you take the standard deviation and you divide it by the mean. Okay, So it's the standard deviation divided by the mean. So I'm going to write this up here. So we have our formula. Okay. So, we're going to take a look at number 10. Okay. And so we've got a National Public Health Agency states that the mean height for adult men is 71.6 inches. So we're going to get men here. And we have their height. The average, which is mu, is 71.6. The standard deviation is 5.3. For weight, we have 197.2 with a standard deviation of 41.8. Okay? So the concept here with this one is these values are smaller because we're talking about height and we're doing it in inches, but we've got weight that's a lot higher on the value, okay? So they ask us to compute the coefficient of variation for the height, okay? So that's going to be 5.3 over 71.6, which is 0.074. And then they ask us to compute the coefficient of variation on the weight, okay? So that one is going to be 41.8 over 197.2, and we get 0.212, okay? So they ask which one has a greater spread relative to its mean. You're looking for the higher coefficient. So this one has the greater spread, okay? Because its coefficient of variation is a higher value than the one for height.